Hello. Can the people online hear me? Yes? How about YouTube online? Possibly. Oh, okay. While we wait for the 15-second delay on YouTube. I just want to say, today is really about you and celebrating all of the work you've done this summer. Well, really the next 3 days is really a celebration. So as much as it is, and we recognize that getting up and speaking about the research is a scary moment. Do know you are ultimately in a safe space to speak your mind on your research and do the best you can. And feel free if you have any nerves before your thing and you need a moment to just take water, take a breath, always take those moments. We know we gave you 20 minutes, but ultimately if you need a second just to breathe, you have that time. So I'm looking forward to seeing everybody's work today. And for people I haven't seen yet, hello, I got in yesterday, so I'm here now. And yeah, James, do you have anything to add? You want the microphone?
I feel like I should say something since everyone else is. Yeah, we're all proud of you. What about them? Oh, posters will be done soon. We're running into complications. So
The printer ran out of paper.
we're
It's not a kind of thing. So it's going to take one.
yeah. I know we said that we would start printing on Tuesday, and that is true.
We did. We printed a bit about.
And I'm sorry if that made you think that we would be able to show them to you on Tuesday. We did this in advance so that any complications that arose would be dealt with before 9:30 on Friday, because that could be bad. But they're going well. So posters will be done soon. Other than that, I don't know, do your best, share your science, and we're really, looking forward to what you've done.
And one more announcement, shirts are done. I got word this morning. And we're going to try and get them to you on Thursday, like afternoon Thursday, but worst case, you will get them Friday, no matter what. Yeah, and I will get you a price momentarily. I'm waiting for them to tell me the grand total. So, okay.
All right, so it seems like this mic should be working. Yep. Yeah, I think we ran the other one out of battery with all of the testing this morning. Technical complications, folks. This is what science is. Okay, awesome. All right, then we're going to get started a little bit early because inevitably things run behind. So we're going to get started with Amelia Lee.
Hi, everyone. My name is Amelia Lee, and the title of my research this summer was Thermospheric Molecular Oxygen Densities via Stellar Occultations Measured by Source. My mentors are Josh Elliott and Ed Beck. So occultations have been used to study atmospheres for a long time. This figure shows different satellite measurements at different altitudes, studying the thermosphere throughout the years. There have been several studies conducted on molecular oxygen in the Earth's thermosphere at different altitudes. However, most of these were done by solar occultations and were thus constrained to dawn or dusk. So why is the thermosphere important and why are we studying it? The thermosphere is the uppermost layer of the atmosphere from about 100 kilometers to 600 kilometers above the surface of the Earth. Much of the X-ray and ultraviolet radiation from the sun is absorbed in the thermosphere, which can lead to the expansion of the thermosphere. And that just means that the top of the thermosphere isn't very well defined. This also impacts the gases in the thermosphere. In fact, photoionization from solar radiation begins to break down molecular oxygen into oxygen around 100 kilometers. There are many satellites in orbit in the thermosphere, so it's important to know about the structure and the gases in it. It's the closest part of the atmosphere to the sun, and as seen in this figure, solar activity influences the temperature in the thermosphere. Around a solar minimum, it's about 800 degrees Kelvin, and around a solar maximum, it's about 1200 degrees Kelvin. I think this figure is very good. It shows how far down certain types of solar radiation can reach into the atmosphere, as well as how the density of major atmospheric gases changes as a function of height and the temperature of the thermosphere at a solar maximum and solar minimum. So how are we taking these measurements in the thermosphere? In this project, we are using stellar occultations. Stellar occultations use starlight to probe the atmosphere of a planet by measuring the change in the star's irradiance as it sets or rises relative to the satellite. In measuring the change in irradiance, we're taking the spectra of the star as it sets and rises in the atmosphere and as the light passes through the atmosphere. And thus we are measuring the absorption of the light by the gas in the atmosphere. In the case of this research, we are looking at molecular oxygen in the Earth's thermosphere. The spectra of the star changes as the star sets or rises, and this can be used to quantify the type and amount of any particular gas in the sphere when compared to the star's original spectrum. Something to note is that we locate the measurements at the tangent point because it's the point of closest approach of the satellite, of the line of sight between the satellite and the star. The density of gas is highest here because the density of gas falls off exponentially radially. So much of our contributing measurements of the column density come from this area. You might be asking why make these measurements with stellar occultations and what's the difference between solar and stellar occultations? Well, occultations can be done with any source of light, sun or star. However, there are some advantages to using stellar occultations when you can rather than solar occultations. The first is that solar occultations are limited to dawn or dusk because that's when the sun sets and rises, and there are no such constraints with stars. And the second is that the sun is very large, and so its size must be considered, whereas stars are point sources and their size does not need to be considered. And finally, occultations are not just limited to the Earth's atmosphere or even to atmospheres in general. They've been used to study the atmosphere on Mars and even Saturn's rings. The Solar Stellar Irradiance Comparison Experiment, or SOLSTICE instrument, aboard the Solar Radiation and Climate Experiment, or SORCE satellite, took both solar and stellar occultations, with the stellar occultations being a calibration of the instrument. It took 12 solar occultation scans over a period of 2 months in the summer of 2004, and 818 stellar occultation scans over a period of 7 years from October 2003 to October 2010. It took these scans consistently over the 7 years, so there are many scans spread over each year. It used the light from many stars as a calibration, but the irradiance of these stars were pretty constant, around 10 to the 10 photons per second per meter squared. Measurements for the stellar occultation scans were taken in the far ultraviolet range at wavelengths around 140 nanometers, which absorbs molecular oxygen. It took these measurements at altitudes ranging from 20 kilometers to 600 kilometers above the surface of the Earth. But the data we are focusing on is in the lower and middle thermosphere, so around 100 to 250 kilometers. And this summer's research is looking at the stellar occultation scans, but this work is actually built on last summer's REU research by Claudia Luna, who analyzed the solar occultation scans from source. And what's also cool about this data is that since it was a calibration data, it has been largely untouched until now. So we had two main goals this summer. The first was to obtain number densities for molecular oxygen in the middle and lower thermosphere. And the second was to show a correlation between number density and solar activity. The number density is the density of atoms in a given volume. So it's a good indicator of the scale, height, and structure of the atmosphere. Our first step was to plot the irradiance versus the time series of each scan. Each scan was taken on a different day over different times and with different stars. So each scan will look a little bit different. This scan was taken July 13th, 2009, and each of the following plots and calculations in this presentation were made from that data, but all of these plots and calculations were repeated for every scan. This figure is the irradiance versus the time series, and it gives us a good look at an occultation. As you can see, as time progresses and the star sets or rises, I think sets, the irradiance gets lower. So the next step was to find the extinction ratio, which shows how much irradiance is absorbed. And it's just the measured irradiance at a given tangent point over the irradiance at the top of the atmosphere or at the top of the highest tangent height. This plot is the extinction ratio plotted against the tangent height. And as you can see, the ratio tapers off around 150 kilometers, which just tells us that the atmosphere is becoming more opaque there. And so the irradiance at the top of the atmosphere is much higher, which is expected. There's less light getting through the atmosphere. And finally, there was initially a lot of noise in our data, so we did a boxcar smoothing on the extinction ratio. Initially, there were some values in the extinction ratio higher than 1, which just indicated that there were irradiance values at a given tangent height that were much higher than the irradiance at the highest tangent height. And that would cause problems in our calculations later. So that's why we did the smoothing at this step. So the first step to finding our number densities is to find the column densities. The column density is the density of atoms along a tube between the satellite and the star. It's measured in units per centimeter squared, so it's an area. The equation at the top of the slide is the equation we use to solve for the column densities. You just solve for NO2. ER is the extinction ratio, which was already calculated, and sigma is the O2 cross-section, which is the effective cross-sectional area as a function of wavelength, or the cross-sectional area that a photon is likely to interact with. The image below gives a visual representation of what the column density is, and basically we are just trying to find the density of atoms along that tube. The column density does not give us very much information about the scale, height, or the structure of the atmosphere, so by itself, this measurement is not very useful, but it is essential to finding the number density, which does tell us about the structure of the atmosphere. So this is what our column density profile looks like. This is plotted on a log scale, so there's an exponential decay as a function of tangent height. These tangent heights are measured relative to the center of the Earth, and that's why they look much higher, but they're the same tangent heights I was talking about before, about 110 to 250 kilometers above the surface of the Earth. You may notice there's some strange features at the bottom of the column density scans, around 650 kilometers from the center of the Earth or 130 kilometers above the surface of the Earth. And this is just due to the fact that the atmosphere is becoming more opaque, so there's more noise and it's harder to get accurate results. We did a linear fit in the log space on the column density to extend our data to higher tangent heights. The orange line is the linear fit and the blue line is the original data. The linear fit matched up very well with the original data. And this is good because we're using the linear fit in our further calculations. So now we have everything we need to find our number densities. I have repeated this before, but the number density is the density of atoms in a given volume. And this will tell us about the structure of the atmosphere. The original equation to finding the number density is the integral at the top of the slide here, which just says that the column density is equal to the integral of the number density along the line of sight. This is a difficult equation to solve. However, there are a lot of different pieces that go into it. And so the next equation is the matrix version, where L is the line of sight matrix, capital N is the vector of column densities, and lowercase n is the vector of number densities. So to find this vector of number densities, we just have to invert this equation, and we do so by using the Moore-Penrose left pseudo inverse to find the vector of number densities. And this picture at the bottom is a visual representation of the number density. It's the density of atoms in that cylinder. And as you can see, it will vary with height. So these are number density profiles taken from two different scans. The one on your right, I think, was taken July 13th, 2009, and the one on your left was taken July 19th, 2006. Unfortunately, I don't know what stars these are taken from. Like the column densities, these are tangent heights relative to the center of the Earth, but it's the same scale as before, about 110 kilometers to 250 kilometers above the surface of the Earth. These number densities also decay exponentially with the tangent height, and the scale for these number densities was about 10 to the 8 to 10 to the 10 centimeters, units per centimeter cubed, depending on the height. And again, you might be wondering about the strange features at the bottoms of the graphs. And again, that's where the noise of the atmosphere, that's where the noise becomes more large because the atmosphere is more opaque. So it's harder to get an accurate reading down there. There were initially 818 stellar occultation scans, but we found that some of the scans contained multiple occultations at different irradiances and different wavelengths. So we filtered those scans out, and from the scans with only one occultation, we chose 50 of the brightest scans. So there are about 6 scans from every year, ranging from October 2003 to July 2010. Number density values at 120, 150, and 180 kilometers were collected from those 50 scans. So what you see here is the composite solar Lyman alpha irradiance and time series from Lizard to show the portion of the solar cycle we have data for, which includes a solar minimum. The graph you see next to it shows the number density at 180 kilometers plotted against the dates that the scans were taken, which is the same time scale as the Lizard graph. So you can see that there's a similar downward trend in number density as irradiance over the solar cycle. And this is because the density of gas and solar activity are correlated. This is the same Lizard graph as the last slide, but next to it is a plot of the number density at 150 kilometers against the time series. Like 180 kilometers, there's a similar downward trend over the solar cycle. And this is the same Lizard graph as the last 2 slides, only this time the plot next to it is plotting the density at 120 kilometers. And this is where things kind of get interesting. As you can see, there's a large range of values and there's no clear trend in the data. I'll say a little bit on this more, but this may be because the atmosphere becomes more opaque around 120 kilometers. The signal to noise ratio gets lower, so there's more noise, which results in the large spread of data and no clear trend. So finally, these are the number densities plotted against the composite solar Lyman alpha irradiance values. There's a clear upward trend in the 180 and 150 kilometer plots, showing that as the irradiance gets higher, so does the density of molecular oxygen in the thermosphere. Similar to the time series plots, there's a large range of data and no clear trend in the 120-kilometer plot. So finally, the conclusions that we drew were that molecular oxygen density and solar activity are correlated. Number densities decrease exponentially as a function of tangent height. And as I said before, anything above 20 kilometers above the surface of the Earth will show the same trend as the number densities at 150 and 180 kilometers. And anything below 120 will be too noisy to get meaningful results. So 120 kilometers might be a good cutoff point for this data. I want to thank my mentors, Josh and Ed, and also Claudia Luna for all her hard work last summer. Here are my references. Does anybody have questions?
All right, any questions?
So in your measurements, are you always looking at the same spot over Earth when you're going through it, or is it like at different solar local times as you're measuring?
We did not, we were not able to determine the local times. We had the latitude and longitude of the satellite, but that is something that we were not able to look at.
Okay, thank you.
Other questions? If you had another 9 weeks to work on this, what would you add or change?
I would definitely work on finding the local times and looking at the variance of molecular oxygen over the local times. And I would also try to separate the occultations from the scans that had multiple and expand our data set a little bit.
Right. Any other questions? Any questions online? People online, we can see your questions on Zoom or on the live stream. And if you type them in, we can get them in the room. None? All right, then thank our speaker one more time. Right. I'm going to take care of a couple of things here. First, hide these Zoom controls so that folks online can't see it. All right. There we go. Now we will bring up our next presentation. The other thing is for the rest of the speakers, I'm going to be keeping your time. When you get to 5 minutes, I'm going to hold up my hand like this for 5 minutes. When you get to 1 minute, I'll hold up my hand like this for 1 minute and then wrap up. All right. All right. So our next speaker is Gabriel Moraga. I will bring up your presentation right now. All right, everything look good?
Mic check. Yes. Awesome. Well, welcome everybody. My name is Gabriel Moraga, and I am currently a student at the University of Colorado Boulder. I am actively in the midst of obtaining my Bachelor's of Science in Astronomy. The project that I have been contributing to over the past 9 weeks is pushing the frontiers of operational geoelectric hazard modeling. The mentors that have been graciously guiding me are Dr. Wendy Carandy and Dr. Greg Lucas. So I wanted to start with a bit of background information on space weather. So space weather is defined as the conditions that are occurring in the solar system. There are many aspects to space weather, but the coronal mass ejections tend to be the main culprit that get our attention. CMEs occur in an 11-year cycle, and they burst plasma, and that carries a magnetic field into space. That is then carried by solar wind towards Earth. Now, when the strong exchange of energy between the charged solar wind and Earth's magnetosphere, it is called a geomagnetic storm. Earth's magnetic field usually protects us from radiation that these storms bring, but sometimes the charged particles from the sun rattle our ionosphere. These disturbances that occur in the Earth's upper atmosphere and near Earth space are capable of seriously damaging national infrastructure. So now that I have linked the sun to space weather and to Earth, I want to give a brief background on Earth and what geomagnetic activity affects. In the picture above, which was generated by NASA, we can see a few things happening. We can see that spacecrafts, satellites, GPS power systems, and even pipelines on the ocean floors are all affected by space weather. So current research is trying to solidify a solution that will determine where and when geomagnetic induced currents, also called GICs, may impact society's infrastructure. GICs are a space weather-driven phenomena that are driven by geomagnetic disturbances. With all of that said, Earth's power grid infrastructure is conductively tied to geomagnetic induced currents. Assessing and mitigating geomagnetic disturbances is crucial. Well, why, you might ask? Historically, space weather has affected Earth. We have seen this in several events, but the Carrington event and the 1989 Quebec blackout that lasted 9 hours are the two that get the popular vote. Humanity has built a world in which power grids are essential. So measuring GICs is important. And currently there are 30 ground-based real-time stations across North America that measure surface geomagnetic field data. And those are used for input to generate geoelectric field maps. The picture above is the station located here in Boulder, Colorado. And the instrument on your right is one of the surveying tools at this observatory. Every observatory station has a basic package of a triaxial fluxgate magnetometer for gathering vectorial data and a proton magnetometer that measures the total intensity of the magnetic field. The two instruments are sensitive to temperature and magnetic interference. So with that said, the buildings of each observatory are situated on plots of land that are sufficient in size, and that helps with isolating the operations from outside magnetic interference. So the map above is a geoelectric field map that was produced by a collective effort by USGS, NOAA, NASA, NSF, and international partners, NRCan. The map is generated in a multi-step process, beginning with collecting real-time vector geomagnetic field data from these observatories that are spread across North America. The importance of a geomagnetic field map is to predict and monitor the surface magnetic field. Since stations are spatially separated, the magnetic observations are interpolated at a clean-cut 2-degree longitude-latitude grid. This map was produced in 2019, and it stays as a current operational geoelectric field map. It has proved to be successful in the United States' ability to support the power grids industry and mitigation of hazards related to geomagnetic disturbances. There have been many upgrades and machine learning systems put in place to make this map more accurate. Upgrades in interpolation methods were made by looking at bilinear and nearest neighbor methods. Now, even though this product is producing great measurements, there's still no method in place to deal with anomalies or missing data. So the triaxial fluxgate magnetometer that I mentioned 2 slides ago gathers data with a directional component and a numerical component. The vector component usually consists of a horizontal intensity, declination, and a vertical component. The data that I have been looking at is historical time series data, which consists of X, Y, and Z variables. These components are geographic north, geographic east, and geographic down. The reason these variables are important is because they are what is needed to generate geoelectric field maps. All of the data sets that I've been looking at are open sourced and come from NetCDF4. Now, since this data is time series, it is measured in a 1 second scale, and also means that this data, the shape of it is usually in the millions to billions. The variables are also measured in nanoteslas, which is a measurement of magnetic flux density. A nanotesla is an SI unit, which is also an internationally used metric unit. The measurement of magnetic flux is important because it basically shows how strong the magnetic field is at a point. When we correspond this to space weather affecting our atmosphere, we can see where it is the most and least intense at a point. The reason historical data is important is because it has already happened, and it is a good baseline to build a forecast method from. It also gives insight to seasonal trends, missing data, anomaly trends, and historical regional magnetic flux density. I've specifically been looking at a small window of data so I can build a statistical analysis model before I run it on the whole data set. So the main goal for this project is to use and research historical data to generate machine learning algorithms. These algorithms will take historical data and train the machine learning models so that future predictions are based off of past observations, thus generating a more realistic interpolation output, and that can be run in real time. So with all that said, the main goal, like all of that going into the project, I had to start somewhere. And building a statistical analysis model was an interpolation model was where I needed to start. When starting this REU program, I had very little knowledge of Python, and that was a learning curve, but it's been a fascinating journey. After trial and error, I feel like I've started to really understand the power that Python has. Since the data I am working with is a historical time series data, using a statistical method that was a baseline for my priority. Reason being that statistical analysis model would be able to show me trends and a seasonality of the data. A statistical model would also show me if the spread was significant or if it was just an expected variation of trends. I set the standard deviation to 3 because there's a wide range in values in the time series, and this would allow for friendlier interpolation and anomaly detection. Now, the graphs on the next few slides are set to only see data between March 11th and 15th of 1989. Why this date? Well, this is the date of the 1989 Quebec blackout. And it was an area of interest during my start of the REU. This can also show us how the solar storm affected different parts of North America. In the graph above, I have generated code to identify where the missing data is. Now, data that is missing can be caused by many things, like local internet disturbances, local power outages, and even cars driving by. Now, this window of time is showing a function that takes the data and uses the NumPy library in Python to return these NaN values as 0. Then I just moved the dropout in the red to a value closer to the data to better understand why this dropped out at the certain nanotesla measurement. It is important to flag these NaN values because knowing where these gaps are will help with interpolation. Previous methods have just removed the data, which has been an issue in generating geoelectric field maps. So now that we know where the gaps are, we can implement interpolation. In the beginning, I started with a linear method, and I found out that this wasn't working for me. Reason being that this data estimate resulted in the same output of when the data was just removed. The cubic interpolation is a more realistic method because it not only looks great, but it also has continuous derivatives between points. This means that there's a rate of change of the function to one of its variables. This interpolation method is a smoother and has smaller errors. This method also is a better estimate because the gap does not have to be removed now. However, it is just an estimate between values. So being able to refine this in the future would be ideal. Detecting anomalies in a data set is important for 2 reasons. First, it can show outliers that are unwanted and that we can clean up. And second, it can also show points of interest and allow for further investigation. Anomalies are also dependent on the standard deviation, resulting in finer anomaly detection. Above, you see 2 separate graphs. The one on the left highlights the anomalies showing at X, and the standard deviation threshold, which is the yellow. This window of data is also a snapshot of a 2-hour window, and those anomalies are points in the data that breach the threshold. The bottom graph is just a graph of the rolling standard deviation to confirm that the breach is, there's a breach on the threshold. The graph on the right is zoomed out and has a window of 4 days. So we can see that there's plenty of anomalous data. The anomaly detection method is a function in Python that uses the rolling mean and rolling standard deviation to calculate a bad value. This bad value is what is flagged and that outside of the threshold. Now, this graph is from data collected in Fredericksburg, Virginia, and it is showing that there were massive spike in magnetic flux density. And we see anomalies leading up to the event and after the event. Understanding why will be a future endeavor. So the end result is a combination of flagging NANs, filling gaps with interpolation, identifying anomalies, and confirming them with the rolling standard deviation within a time frame. With all these methods, synthetic data can be used to make better estimates on what the data will look like without removing it. The statistical method model can also be used on whole data sets for a wider analysis of a time series data. Having this end result will allow for easier analysis for each observatory's historical data. Now, in the future, I will be continuing to work on this project, and I will get started building algorithms that can be trained into machine learning models. I will use my baseline statistical analysis as the base. I've started looking at Profit, which is a forecasting model, and scikit-learn to jumpstart on understanding that machine learning. I would like to acknowledge all of these wonderful humans because they have given me knowledge and helped me succeed throughout the summer. Any questions?
All right, thank you very much. Any questions? Yes.
So I have 2 quick questions for you. The first one is simplistic. What is a NAN? What does that mean?
Yeah, so the question is, what is a NAN? And a NAN is where there is no data at all. So the magnetometers are still reading the data, but then there's like a dropout. So then there's no data, and that is what a NAN is. It's not existing.
Okay, I see. And my other question that I had was on your standard deviation slide. My other question is, what is defined as a bad value?
So what is defined as a bad value? So a bad value is mathematical statistics, and that is when you are plus and minusing the statistical mean and the standard deviation on both sides. So that bad value is what is outside of each of those.
Okay.
Yeah.
Thank you.
Thank you.
I'm wondering if your methods will work in real time. You've kind of described right now how you're reprocessing this old data, and will your methods be able to be used in real time?
So that is a great question. Will this model be able to run in real time? So currently this model I have built is based off historical data that starts like 1975, some data sets, and they usually all end around 2015. So the end goal is to pre-process more current data, so then it becomes up to date and can be run in real time eventually. Thank you.
Hi, I have a question about your standard deviation slide where you had some X's for anomalies. And I was wondering if like you looked into those anomalies at all and have any like thoughts as to why those were anomalies or whatnot, or what was anomalous about them?
Yeah, so as the question is, what is anomalous about the X values? And if I looked into them, as I answered Bryce's question, those are just a statistical calculation. But through the research I've done, it tends to be there's a spike in anomalous data before and after an actual spike at big solar storm events. So I don't really know why that is happening, but it definitely was an interest that I was like there, because I picked up with that too. And I was like, there's something happening before these big events. Thank you.
That's something to follow up on at AGU.
Yes.
All right, thank you very much. Let's thank our speaker again. All right, folks, we're coming up on a break right now. So they're setting up some coffee and tea out in the lobby. We're gonna turn off the sound and the video to the live stream right now. So if you're online, you're gonna see us go dead for a little while, but we're gonna keep the live stream going. So we'll be back here, it looks like at 11 o'clock with Reese. So Reese, if you could just be in the room and ready to set up at that time. The rest of you, we're gonna take a little break, recoup, and we'll be back here at 11. Thank you. All right, folks, welcome back from the break in the room. If we could quiet down. So our next presenter is going to be Reese. A couple of notes to the presenters. Now, James is going to be keeping time, so look to James for your 5 and 1 minute warnings. So I'm going to hand it over to Reese now.
Thank you. Hopefully everybody can hear me. All right, so hi, I'm Reese Van Putten. I go to Florida Institute of Technology to study astronomy and astrophysics. My mentors are Dr. Xiaohua Feng and Dr. Naomi Maruyama. And we did a project on evaluating the accuracy and the limitations of the Robinson formulas as a method of calculating ionospheric conductance. So just starting off with some of the key takeaways from this project, and we'll get back to this. What we do is we investigate the dependence of ionospheric conductance, Peterson and Hall conductance, on both precipitating electron energy and also on the background conditions. Peterson conductance is generally less sensitive to background conditions than Hall conductance is. That was one of our findings. Another one of our findings is Hall conductance significantly decreases with increasing solar and geomagnetic activity, which we found is kind of strange. And then our results show that the Robinson formulas may produce considerable error in Peterson Hall conductance estimation, especially in the lower energy range, 1 to 3 keV of precipitating electrons. And then just some background. Here we see the ionosphere. So it's basically nested between the atmosphere. Well, it is an atmosphere layer right beneath the magnetosphere. And as you could have guessed, it is made of ions. It contains a lot of ions. It's 80 to 500 kilometers in altitude. And because it has so many charged particles, electrons, protons, and ions, there's a conductivity. So looking at these lines on the graph to the right, we see there are a bunch of field lines. So all these charged particles follow these field lines. You can kind of think of conductivity as like a wire. Okay, so electrons move along a wire, producing electrical current. And depending on the current and the material that you're using, you're going to have a different conductivity. In this case, we're not looking at wires though. We're looking, our medium instead of like silver or copper is a neutral atmosphere. You can see that Peterson conductance is much more relevant at high altitudes, whereas Hall conductance stays much closer to Earth at lower altitudes. And the charged particles that we're looking at specifically are auroral precipitating electrons. That means that electrons are falling from the magnetosphere into the atmosphere. And that's actually what aurora are. So like aurora borealis, that's what you're seeing is precipitating electrons. Significance of this research, the Robinson formulas are widely used for space physicists, but we don't know how accurate it is and we don't know its limitations. They have not been assessed yet. And that was one of our purposes, is we're assessing the Robinson formulas. Ionospheric conductance is critical to our understanding of magnetosphere-ionosphere coupling, the geospace environment, and space weather. So here are the Robinson formulas up in the top left. The most important thing, the only takeaway you really need for that is that it is related to the average energy of precipitating electrons. And what that means is if you look at the x-axis on these graphs, you see 1.0 keV. There it is, the electron energy follows a Maxwellian distribution. And 1 keV is the average of that electron distribution. So then 10 would be another Maxwellian where 10 is the average. And then incident energy flux will describe the power of the precipitating electrons. And looking back at the graphs, the dashed line are the Robinson formulas and the solid line is what the Robinson formulas were, Robinson paper was trying to fit to. Okay, and that's a Vic-Ray 1981. That's the solid line. There are some questionable things about the study, though. It was from 1987, and it fit to a very limited amount of observational radar data. It was 3 days of incoherent radar data, and it also uses a very simplistic empirical electron impact ionization model. What electron impact ionization means is when those precipitating electrons come down, fall into our atmosphere, it will collide with neutral particles like oxygen, for example, and then it will ionize. That neutral particle will become an ion and expel an electron, which adds to the conductance. Another thing is that the dependence on background conditions were never considered in this paper. So background conditions include things like magnetic field, latitude, longitude, and solar and geomagnetic activity. The observational data was all taken at a quiet time, so a quiet period. There wasn't a lot of solar or geomagnetic activity. So because of all these reasons, the accuracy of the Robinson formulas has not really been quantified. So our goal is to use more sophisticated models to calculate Hall and Peterson conductance to evaluate the accuracy and limitations of the Robinson formulas. So this is the first of the empirical models that we use that's more sophisticated. This is our ionization rate model that we used, Fang 2010. The one that Robinson used was from 1963. Computers were pretty new then. So, and again, what impact ionization is those precipitating electrons collide with the neutrals. I have a little graph down here. Imagine energy, the precipitating electrons carry energy. There's a collision and it creates an ion and a free electron. So this method is more accurate. And if we look at this graph, something important to note is that at lower average energies, it has the ionization rate is of smaller magnitude than higher energies. So if you look at the blue line, it's a lower magnitude, but it extends to higher altitudes. And that's a pattern that we're going to continue to see. And another thing to note is that average energy, we are considering a Maxwellian curve again, just like the Robinson formulas were. Our next empirical model that we use is NRL EMSIS 2.0. This describes atmospheric neutral densities. The neutrals that we're looking at are nitrogen oxide, nitrogen gas, and oxygen gas. And it's used to calculate ionization rates. So here we have, or excuse me, I said nitrogen gas and then oxygen, mono oxygen. So the solid line is on the day side at 0 longitude, and the dashed line is at 135 on the night side. And you can see that there is a small difference in the densities at these different points. Our next empirical model is the IRI 2016. This describes charged species branching ratios. The ions that we're looking at are NO+, O+, and O2+. So this red line right here is the summation of all the collisional frequencies of those 3 ions. There are other ions present, but they're in very small amounts, and they're deemed generally not significant to the conductance calculations. And then this blue line is of the electrons. So you can see that the electron collisional frequency is about 1 magnitude larger than the sum of the ions, depending on the altitude at least. Using this model, we also calculate the branching ratio, which is helpful in finding the number density of electrons. Here's the IGRF 2013 model. This describes magnetic field strength. And it's also used to calculate the gyro frequencies of the ions. Here we have a latitude longitude map with the yellow color being the highest and the kind of purple being the lowest values. And it's important to note that this is actually the reciprocal of the magnetic field. So it's in units of 1/Tesla, not Tesla. The reason I do this is because the conductivity and conductance are inversely related to the magnetic field. So you can see at noon, at 0 latitude here, we have the highest values of the reciprocal of the magnetic field. And then at the exact opposite point at midnight, we have the second highest values. Those are the highest regions. At dusk and dawn, they're quite low. Now we can actually calculate the conductivities. So getting more into what the difference is between Peterson and Hall. So the Peterson conductivity, the direction of the current flow, the field lines, it's perpendicular to the magnetic field and parallel to the electric field, whereas the Hall is perpendicular to both magnetic and electric. Again, some important thing to note, just like the ionization rates, you can see this blue line, that's at lower energies. It extends to a higher altitude, but its peak magnitude is lower. And then looking at the purple line, again, it goes, it extends to a lower altitude and has a higher peak value as well. And the Hall, we can see that happening as well to a little bit lesser extent. Peterson conductivity is much more significant at higher altitudes. Hall conductivity breaks out, becomes kind of insignificant around 200 kilometers. And what we can do is we can integrate these conductivity graphs by height, by the altitude, and we will receive conductance. The reason that we're using the energy range 1 through 15 keV is because we can assume photochemical equilibrium. So like I said, we can integrate those conductivity plots and then we receive conductance. This is spatial variation. I don't know how well you guys can see the numbers in the back. Is a big screen, but each plot, the left side is Peterson, right side is Hall, but each plot is at a different average energy. So it goes 1, 2, 5, 10, and 15 keV. The top of each plot is at noon. The bottom of each plot is at midnight. And you can see again, just like the reciprocal of the magnetic field, that the highest conductance values are at noon and the lowest is at midnight. We can also see that the maximum conductance values are higher as you go down to higher precipitating electron values. And then the variance is also highest at lower energies. So these are all normalized plots. They don't give the real values. So you can see that in these lower energies, you have a much larger variance on the color bar, whereas down here it decreases. Here is a chart from another paper from 2004. This is what the real conductance looks like. This considers photoionization and electron precipitation. We're only looking at electron precipitation. So you can see on this day side, there is plenty of ionized particles that we're not seeing because this is from the sun and extreme UV light ionizing. And another thing is that we are looking at evenly distributed energy levels. This is not. We're separating it and partitioning it. The 2004 paper is not. So then we want to, this is looking at the different variation with solar and geomagnetic activity. So then each little box right here is averaged out through latitude, longitude. So if you were to take those dial plots and condense them into one little box in these chessboard plots. Same convention, lower energies to higher energies, left side is Peterson, right side is conductance. On the x-axis, we have the AP index, which is the geomagnetic index. So it's ascending to the right, higher geomagnetic activity on the right. On the y, we have ascending F10.7 index, which is the solar activity. So you can look at these graphs and start to notice a little pattern. On Peterson's side, on the top right for most of these graphs is the highest Peterson conductance. That means at high solar and geomagnetic activities, we end up with the highest Peterson conductance. But for Hall, it seems like it's the opposite. On the bottom left, where we have the least amount of solar and geomagnetic activity, we have the highest conductance. And then at high activity, we have the lowest. We don't really know why this is because it seems counterintuitive. The more electrons that you have, the higher conductance we should have as well. So that's something strange that we need to look further into, but that was one of our findings. Another interesting thing to notice is that, again, these are normalized. So if you look on this color bar, the Peterson conductance varies about 5 to 10% from maximum to minimum for all of these. Whereas Hall, at low energy, this is varying by about 21%. At 2 keV, it's varying by about 11%, and then it sharply decreases to 4%, 2%, 1%. So we see at low energies, Hall varies quite a bit and then drops off to being very stable. Peterson varies 5 to 10% throughout. And then if we look at both spatial and background variations, the last two slides, we'll look at both of those variations at once. We get this plot. So this green line is the Hall conductance variation. And again, we notice this convention that at low energies, it is very variable to the background changes and spatial changes. Whereas Peterson is pretty steady. It starts higher up at low energies, but then it really like evens out right here. Seeing this blue line. We also see that Hall intersects and becomes more stable and less variable than Peterson at around 6 keV. So here's our results. This, in each graph, the red inner line is our results, the average plus or minus 1 standard deviation. And that average is considering both latitude, longitude changes and the background conditions. Whereas the pink is the maximum and the minimum. And then this black line is the Robinson formulas. So you can already start to see some of the limitations that the Robinson formulas have because it doesn't show any uncertainty or any variance. It's just saying this is what it should be, but we don't know what the uncertainty actually is. Our results and our method shows what uncertainty there might be and what variation there is. The blue triangles is the Vickrey 1981 from the Robinson slides earlier. That's what Robinson was trying to fit with. And you can see that there's even a lot of discrepancy between the Robinson formulas and Vickrey graph, which is interesting. Again, 1987 computers weren't as good back then. We notice this graph right here shows the percent discrepancy specifically with our method, these red lines, and then the black lines. And you notice that there is a huge discrepancy at 1 to 3 keV, reaching almost 65% right here, variation. And then it starts to even out again. And you can see on these plots as well, it doesn't even, the Robinson doesn't even fill in with the red. There's no overlap. Other things to note is that most of these papers for Peterson conductance peak at around 3 keV, whereas Robinson peaks around 4 keV, showing that Robinson might not be the most accurate if all these other papers are disagreeing with it. These green dots, that's from the 2004 paper, Cummins et al. And it's important to note that this was done at a high solar activity. And we can see that with Peterson, it's a little bit above our average. With Hall, it's a little bit below our average. That's consistent with the dial plots or the chessboard plots that we have earlier, where Hall is lower at higher solar and geomagnetic activities. So again, just going over the key takeaways, what we did is we investigated the dependence of ionospheric Peterson and Hall conductances on both precipitating electron values and also on the background conditions. We found that the Peterson conductance is generally less sensitive to background condition changes than Hall conductance is. Again, that's kind of strange. We don't know why that is. And we also noticed that Hall conductance significantly decreases with increasing solar and geomagnetic activities, which seems counterintuitive, but that was our results. And our results show that the Robinson formulas may produce considerable errors in Peterson and Hall conductance, especially in the 1 to 3 keV range of precipitating electron energies. So our further steps for research is explore why Hall conductance is inversely related to solar and geomagnetic activity, explore why Peterson conductance is less sensitive to background variation than Hall is, and after we do that, we're going to derive new formulas to improve the Robinson formulas, and it will also include a better understanding of the uncertainty behind it. Acknowledgements. Thank you, Dr. Fang. Thank you, Dr. Naomi Maruyama. And thank you to the NSF for funding these projects.
All right, thank you, Reese. Any questions? Yes, Allison.
Nice talk, Reese. So I just had a question, like I kind of have two questions. One of them is more conceptual, but what is the difference between conductivity and conductance?
Yeah, here, let me just go back to there. No, past this. So conductance is if you height integrate the conductivity. Conductivity is material specific, but it's not dimension specific, and it's in the units of Siemens per meter.
Gotcha. Okay, so conductivity is what you measure and then you integrate it to get conductive. But how,
Yeah.
so I guess like, because that line is a curve, do you have to take, like when you integrate it, do you have to take like a line integral or something? Because it's not like 1-to-1.
Well, hold on, I'm a little confused because I flipped the axes because it's not a function right here just because I make altitude on the y-axis, but we're integrating by altitude. We're integrating by the independent variable still.
Gotcha. Okay.
Does that make
Cool.
sense?
Yeah, that
Okay.
confused me a little.
Yeah.
Thank you.
Other questions? Yes.
Yeah, that was a great talk. So I just wanted to double check because along with having computers that maybe were less sophisticated in the 80s, like you were using different empirical models, right? To relate these conductivities to background conditions. So presumably you also are then being able to use like decades more satellite observations that have been incorporated in these models.
Yeah.
Okay, cool.
Easy question. Thank you.
Maybe one more question. Anybody? All right, let's thank our speaker one more time. All right, next up we have Joanne.
Like here.
Am I good to go? All right. Hi, everybody. I'm Joanne Jones. I'm a junior at Case Western Reserve University. I'm majoring in physics and astronomy. And this summer, I was working with Dr. Sergio Vidal Luengo and Dr. Lauren Bloom to use power spectral density and a machine learning technique called a self-organizing map to detect precipitation bands observed by SAMPEX. So before I get into Yes. Can you hear me? Okay. Before I get into the methods that we use, I want to give a little bit of background into where we are looking with this study. So we're looking into the Earth's magnetosphere, and you can kind of see how the Earth's magnetosphere is separated into these different areas, and these are kind of separated by the Earth's magnetic field lines. And you can see the solar wind coming in on the left, and high energy particles from the solar wind come in and they start to spiral along these magnetic field lines. This is due to the Lorentz force. And the high energy particles that we're interested in are found in the Van Allen radiation belts. And you can kind of see them right there, separated by the field lines coming out of the north and south poles. The high energy particles that we're interested in are called relativistic electrons. Relativistic electrons are electrons with energies greater than around 1 mega electron volt, and they're sometimes called killer electrons. And these are found spiraling along the magnetic field lines. Sometimes these electrons fall down to the Earth's atmosphere, and this is called relativistic electron precipitation, or REP. And this can come in a couple of different forms, and I'll get into that in a bit. Why are we interested in this? Well, for the general public, these precipitating electrons cause the aurora, which is really cool. They're also, more importantly, nicknamed killer electrons. These can damage spacecraft, cause satellites to fail, so this affects cell phones, television, the internet, and most importantly, GPS. So much of our daily lives rely on GPS. And for scientists, we are interested because we have a general curiosity about the radiation belts, the magnetosphere, the dynamics about the Earth's magnetic field. We want to understand, why does this happen? And why can the electron content fall so drastically from the outer Van Allen radiation belt? So, sure. Okay. Sorry about that. So how are we studying these electrons? We're using a satellite called SAMPEX. SAMPEX stands for the Solar Anomalous and Magnospheric Particle Explorer. It was launched in 1992, and it was actually only expected to stay up until the year 2000, but due to a quiet sun, it actually lasted 12 more years and stayed up until 2012. This satellite traveled in a low Earth orbit, and it measured the electron count with its Heavy Ion Large Telescope, or HILT instrument. And that's what we're interested in, is the electron count data that we got from it. Here's a nice picture of the satellite. And here's a better illustration where you can kind of see the instruments a little bit better. You can see HILT. That's the instrument that we're using. And using the data from SAMPEX, we can look at these different types of precipitation that I mentioned earlier. First, let's talk about microbursts. So microbursts are rapid bursts of precipitation that are observed by SAMPEX as lasting milliseconds. So here you can see these rapid bursts shooting up and down. Those are the microbursts. They often occur most often on Earth's dawn side during periods of strong geomagnetic activity. We believe that Whistler mode chorus waves, which are naturally occurring electromagnetic emissions in the magnetosphere, are causing these microbursts. We think that they're pretty well understood. We think we know why they happen and how they affect the dynamics of the radiation belts. So that's not going to be the main focus of this study. We're looking into precipitation bands. This is a longer duration form of REP, typically observed by SAMPEX, lasting tens of seconds. You can see a good example of one over here, the long burst up that is lasting about 30 seconds. They're observed during both active and more quiet times. They span through both afternoon and nighttime. And during quiet times, they may be associated with electrostatic waves. And during active times, they may be caused by EMIC waves or electromagnetic ion cyclotron waves. This form of precipitation contributes significantly to the loss of electrons from the outer Van Allen radiation belt, yet their origins are not clear. But we really want to understand these. So What we are doing is developing a consistent way to detect precipitation bands so that we can use the timestamps on these bands to aid future studies in uncovering what could be causing them. We accomplish this by using power spectral density and a machine learning technique called a self-organizing map. And before I get into how we did this, a brief introduction on what a self-organizing map is. A self-organizing map, SOM, or Cajonan map, named after the man who invented them, is an unsupervised machine learning technique. This artificial neural network utilizes competitive learning, which means that each of these nodes are competing against each other to receive the input. It classifies inputs by putting them into bins based on their similarity to one another. If two inputs look like each other, they're likely to be put into the same bin, which is exactly what we want because we want to find all the precipitation bands in one area. It does this by using weight vectors and Euclidean distance in order to determine a best matching unit. And I'll get into that a little bit more once we talk about how I'm using it. Okay, getting into what I did this summer. So first, I needed to filter the data. You can see a full day of data up here on the top, and there's a lot going on here. Visually, there's nothing we can really identify, just a lot of electrons. It's counting the electron count on the y-axis. So we need to get this down into more manageable intervals. Each day contains over 5 million data points. First, we need to select the proper data from the satellite. For the one we selected, the frequency is 10 Hertz, or we have one data point every 0.1 seconds. Next, we want to put it into 10-minute intervals. This is very important to properly filter the data and capture the events, because up here, you can't identify anything, but once we put it into 10-minute interval, you can clearly see these two precipitation bands and maybe a little one in the middle. Next, we want to detrend this data and remove the moving mean, nans, and gaps in the data. Removing the moving mean is a very important part because it gets rid of this little bump before the precipitation bands that we're not interested in, and it also flattens out all of the noise. So visually, we can identify these precipitation bands, but that is not a good way to conduct research on thousands and thousands of intervals. So we want to use a computer to do that for us, and the computer can more easily detect the precipitation bands when we filter out the rest of this and only have these very sharp peaks in the data. Next, we want to use power spectral density. In preparation for the machine learning process, we need to take the power spectral density of all of this filter data using Welch's method. The power spectral density of an interval containing a precipitation band is easily identifiable by this peak in the lower frequencies. This is another beautiful precipitation band. You can see the filtered data, and here is the normalized power spectral density. But when you look at this data that contains some microbursts and just noise, it still has this peak in the filtered data. But when we look at the power spectral density, it is vastly different from this one. You might notice, like I said, that we're taking the normalized power spectral density, and I'll get into why we do that in a bit. Then we write the data, the power, and the frequency from the power spectral density into of each interval into a file. And that is when we're going to bring in the self-organizing map. The self-organizing map will take the data from the power spectral densities. So now we're ready for the self-organizing map. But how does it really work? I only gave a brief introduction to it, so this should clear things up. So this is a nice visual explanation for how it works. So let's say that this giant cluster of all of these colors represents my file that is full of power spectral density data. Each little pixel can represent a 10-minute interval in its power spectral density. And we're looking for precipitation bands. So let's say that each one that is green is the 10-minute interval containing a precipitation band. The self-organizing map, and this one, for example, selects a 10 by 10 grid of random intervals from this to begin the process. After it selects these random initial intervals, it'll start taking every single other one and find the one that it matches with the best and put it into that bin. And at the same time as putting it into that bin, it will update the weight of the bins surrounding it so that the other ones that are similar to that are more likely to be put into the bin surrounding it. So if we were looking for the green ones, you can see that one has some green in the corner. And as it keeps putting more and more green pixels from that first one into this, the bins surrounding that green corner are going to be more and more green. So we're going to find more and more precipitation bands in the upper left corner. And as we run it more and more, they update each other. We see a clump of blue down here, some pink here, some red here, some green here. So the result of this is we can find all the precipitation bands here. Maybe the pink is some microbursts that all got put together, and maybe the blue is some noise. So over many iterations, it puts data into these specific bins, specific corners that we can find what we're looking for in. So how are we doing this? Once exporting the count data and power spectral density for each 10-minute interval into the new files, we can put it into the self-organizing map. For this run, for this study, we are using 1 month's worth of data, or 4,400 intervals. The self-organizing map analyzes the normalized power spectral density data for each interval and puts them into bins based on similarity, similar to what you just saw before with the colors. So here we can see 2 precipitation bands. They look a little different, but they're both precipitation bands. You see the not normalized, the filtered data in the middle, and below you can see the power spectral density. And even though these precipitation bands look a little different, the power spectral density is the same. And that is why we use the normalized power, because this allows the self-organizing map to classify the data based on the frequency distribution and not just the peak intensity. Because if we didn't normalize it, there's a chance that maybe this peak would have a higher amplitude than this one, or vice versa. And then the self-organizing map would put them into 2 different bins. But when we normalize that, it puts them into the same bin. Because we want all the precipitation bands, not just the big ones or small ones. Next, we need to tune the self-organizing map. So self-organizing maps have a lot of different parameters that you can change to produce the best result, such as how many times do we want to run it, how much data, as in how many days of data, what learning rate do we want to use, what size of radius, and that means how much does this bin influence this bin, how big of a map. These are 10 by 10, and this is an ongoing process. This is probably the biggest part of the self-organizing map, is trying to figure out what numbers to use for all these. So this can be changed, but for this study, these are the values that we used. We used 150 iterations, 30 days for the sake of my computer, a learning rate of 0.5, a radius squared of 2, and a 5 by 5 map. But in future studies, these can be updated for maybe a better result. And this on the side, this kind of shows that how much the different values can change it. So if you look at these on the very left, these are not showing a progression. These are all completely different. They're all a self-organizing map ran for 5 iterations. You can see these ones have a very small radius. So this bin knows nothing about this bin. So they aren't putting themselves into corners together. And once they have a higher radius, you can see they put all the purple down here, all the red here, all the blue here, and that's what we want. You can also see how the learning rate affects things. This doesn't look quite as good as one with a higher learning rate. You just have to find, I guess, the sweet spot for all of these numbers. Okay, so the result of this self-organizing map is a 5 by 5 grid of folders. Each of these folders contains files of data. Combined, they contain all of the data from the 10-minute intervals throughout the month. And this is what it looks like. So this is a color-coded visual of my self-organizing map filing system. In this specific run, most of the precipitation bands are found in the blue files. The yellow files contain mostly noise and microbursts, and the red files represent low-quality data. The other colors, you can see some orange, some green. These represent how the data in some files is a blend of one another, because that's how it works. It puts files that are similar together and affects the files next, or the folders next to it. And so there's going to be some folders that are somewhere in the middle. Okay, so now let's look into these results. First, I want to show some of the yellow files, or the files containing noise and microbursts. So these are a couple of different examples of noise and microbursts. Up top, you can just see some pure noise. Here you can see some noise and a curve that there's nothing useful in that. And here we can see some noise and maybe some microbursts. Luckily, all of these were put together because we aren't really interested in this data for this study. So it's great we're getting it out of the files that we want, or the folders that we want to look at. Let's next look into the low quality data, which is really interesting. Not necessarily useful for us, but it is very interesting. This is due to the satellite having a very low resolution when counts get very high. So you can see on this log scale axis, it's at about 10 to the fourth. And when it gets this high, it isn't as great at putting them into specific numbers. It kind of either puts it in 9,000 or 8,000. So when you zoom in on that data, it's kind of up and down. And that causes some very interesting patterns on the filtered data. And this is not something that we want to use because it's not necessarily the most high quality data. Next, let's look into the things that we were looking for, precipitation bands. So these blue files are where most of the precipitation bands are found, which is great. Now we can use these timestamps at the top. This is the index that the self-organizing map uses on the title, and then year, month, day, hour, minute. And we can use that to use in future studies to determine what may be causing these precipitation bands. So once again, all very different precipitation bands occurring at very different times, but the machine learning technique put them all into the same area for our convenience in locating them. Okay, so now let's discuss the results of this. So the self-organizing map successfully filtered out the noise and the low quality data from the precipitation bands, which is great because the majority of our data is noise and low quality data. However, some precipitation bands were classified into the wrong folder. You could see those folders that were a mix of both. Some microbursts were found within the precipitation bands folders. And this may be due to the fact that sometimes multiple events can occur within the same 10-minute interval. So sometimes there's a microburst and right after that, a precipitation band occurs. And that really confuses the map because the power spectral density is not what it should be for either of those, so they get put together. So to fix that and to further the use of the self-organizing map, we can try to filter out the microbursts for precipitation band isolation. We didn't do this in this study because we wanted to see how the self-organizing map reacted to the microburst. But if we're looking for just precipitation bands, we can try to filter out those microbursts. We can also run it again using only the good data. So maybe only the data from the blue and yellow green files. That would give it a higher ratio of good data to bad data to organize. And we can also fine tune the machine learning parameters a little better if we had more time to run it. So in conclusion, this method of using power spectral density in a self-organizing map does work to classify Sandbox data. And using the timestamps from the precipitation bands isolated in this study, further research can better determine the origins of these precipitation bands so we can understand the dynamics of the outer Van Allen radiation belt a little bit better. This run worked very well to filter out the low quality data and noisy data that we're not interested in. However, further work should improve upon this system in order to sharpen the results. Here's my references. I'd also like to acknowledge my wonderful mentor, Sergio, for helping me out through my first research experience. Also, my co-mentor, Lauren. Yeah, thank you.
Hey, Dan, a question.
Sorry to be very slow here. Can you tell me what the horizontal and vertical kind of scales in the self-organizing maps are really supposed to correspond to?
Do you mean about this?
Not in your specific application, but just in general. How am I supposed to think about the different axes
Right.
in your map?
Okay, so every time you run the self-organizing map, it's going to be different where is what. It's kind of just, in this example, it's a very good way to visualize what data is where. The axes don't really tell you anything. It's more once you look into the folders and you can see that precipitation bands are all found in the left corner. Everything in the top right corner is on noise. The axes are changing every time you run it.
So you're just progressively grouping things to
Yes.
similarity.
And every time you run it, they might be found in a different area on the map.
Okay.
This is just the specific one.
But in starting out, it's just wherever things fall, and then you start to look for.
Yeah, it picks 25 random
All right.
windows and then starts organizing them.
Okay, thank you.
All right. Oh, here, I'll get the question over here first.
Oh, hi, great talk. I'm very interested. So my question is first, what metrics did you use to group those, like, to measure the similarity of these different spectrums?
I'm sorry, could you repeat that?
Because you were saying, you put all the spectra that's similar to one group. So what metrics did you use to say, what calculation did you do to say those two spectra are similar, but not similar?
Right, so let me just pull a couple up to reference. So you can see these two are precipitation bands. What we're using to determine if they're the same is this normalized power spectral density. So it's taking just data files full of the numbers for the power and the frequency. Here's just a graph because I think visual aids are better than numbers. And it's finding the ones that are most similar of the normalized power compared to the same frequency and putting those ones together.
Yeah, that's great. So the second question is like, what's the difference between an SOS? I guess the question is like, you're using SOMs. So have you considered like using similar classification methods instead of SOM?
Similar classification measures.
Right.
I haven't looked too much into other machine learning techniques. This is the one that I guess was the goal the whole entire time of my research here. So I haven't looked too much into other classification methods.
Okay, great. Thanks.
Thank you.
All right. I'll go to Brooke.
I'm curious on what the date range of your actual data you're using. You said you use 30 days worth of data, but I'm seeing in your plots, they're like different years. To me, this is saying maybe the telescope has like different uncertainties in your data. Did you handpick these?
Right, so that's a very good question. So the way that worked is we had these years of data and I picked the data that was the most consistent, which was a straight year. But then when I started organizing them, the self-organizing map didn't pick a exact, because I guess the order of the days doesn't matter. We're just like precipitation bands in any day for this example. It is just random days from about a 2-year interval that this self-organizing map picks from.
Right. One more short question.
I just have a brief question because you used this unsupervised, right? So you didn't have to make any like train the model at all. You just kind of gave it all the data.
Unsupervised as in it did it on its own. We had code that we had to update and change the code to make it work for our data, change the learning rate. I'm a little bit confused. Could you repeat that?
Oh, just like this, I know like doesn't typically unsupervised mean you didn't have to make any synthetic data to train the model.
Oh, no.
Yeah. Okay.
We did not. We used real data.
Cool.
All right, let's thank our speaker again. All right. Next, let me just look at our schedule here. Next, we have Max.
Test.
Okay, good. Okay. Right, good to go. Okay. Good afternoon or good morning, everyone. I am Max Storing and I go to Indiana University in Bloomington, Indiana. And my mentor is Zhang Chu, and my co-mentor is James Lindy. And today I'll be presenting my analysis of the dynamics of plasmaspheric electrons using a neural network machine learning model. So just to go over a quick overview of this project. So I'll start with giving a background on both the plasmasphere and the neural network model that I'm using. I'll go over the justification process, the data I'm using, as well as go over the error and how it performed against our test data set. Then I'll go over several events from 2013 and see how the model is able to predict these events that are outside of the data set. And we will see how the model predicts the plasmaspheric electron density, as well as the erosion and recovery of the plasmasphere. I'll also discuss whether or not these are consistent with observations of these events, as well as physical explanations of what these events are actually doing. And I'll discuss and conclude my results, and I'll talk about my future work with this project. So first, what exactly is the plasmasphere? The plasmasphere is a region of cold, dense plasma within the inner to middle magnetosphere, which it extends to about 5 to 6 L shells, and L shells are, for our purposes, Earth radii. But anyway, during during geomagnetic storms, the plasma pause, which is the edge of the plasmasphere, will contract and shrink. And this causes electrons in the upper layers of the plasmasphere to erode and be lost to space. And the cold electron density in the plasmasphere can drive higher energy electrons in the radiation belt, and these are also known as killer electrons. And it's important to understand these low energy electrons because the high energy electrons that they can influence will can affect communications satellites that are near the radiation belts. So previous models have attempted to model plasmaspheric electron density, but they are often based on very limited observational data. And this means that, or this also means that many of them are linear fits of statistical data. And this means that they can predict long-term averages of the plasmasphere, but often they struggle with short-term dynamic events like solar storms and substorms. So this model, as you can see, is an older non-machine learning based model, and it's a linear fit of plasmaspheric density. And again, it can predict long-term, but if a solar storm happens and the upper layers of the plasmasphere erode by a significant amount within a short period of time, it's going to struggle to predict that. So then why are we using a neural network? How does it differ from these traditional modeling methods? So a neural network is a series of inputs and then layers and then an output layer. And the input layer has our data input, and each layer is organized into what are called neurons, and each neuron is assigned a weight and an activation function. And depending on the inputs, each node will either activate or deactivate. And depending on the pattern of activation of these neurons in the neural network, we will get a different output based on the inputs. But most importantly, the neural network is dynamic and adaptive to the inputs that you give it. So it will, over time, it'll teach itself and what structure is best, how many neurons go in each layer, and it'll teach itself what weights to assign to each model or each neuron, sorry. So if given enough time and enough model runs, we should be able to get models that are able to predict both long-term averages in the plasmasphere as well as dynamic and short-term changes in the plasmaspheric electron density. So the first thing we need to do is find out what we're going to input into our neural network. And we have a total of 8 parameters. And these, so the first 4 are solar wind and geomagnetic indices. And we chose these 4 because they correlated the best with logarithmic electron density. So we chose disturbance storm time, or DST, which is a measure of the strength of the electric field's ring current around the Earth. We used auroral electrojet indices, which is the magnetic field strength in auroral zones. And we used the solar Lyman alpha flux, which is a measure of solar irradiance at, I think, 121 to 122 nanometers. And then we used the KP index, which is a measure of the strength of a solar storm. And another thing we did with these solar wind and geomagnetic indices was that we assigned what we call time lags to them. So for a given time, it will have these indices for that given time, but the model will also look back in time a certain amount, so it can understand what the status of the plasmasphere was during and before this event. And then we also used 4 positional and time indices from the ERACE, or otherwise known as ERG satellite. We used magnetic latitude, magnetic local time, L shell, and coordinated universal time. So after we find out what inputs we want to use, we need to train the model. And the goal of training the model is to find a specific model that can make accurate predictions of logarithmic electron density, as well as the erosion and refilling rates of the plasmasphere. So the model tested its outputs for R correlation value and error against ERACE logarithmic density data from 2017 to 2019. And then this last slide, this left graph is a scatter plot of the ERACE data versus, or L shell versus the ERACE logarithmic density. And this is a 2D histogram of the L shell versus logarithmic density. And you can see where in the plasmasphere the density is concentrated. So we ran the model about 500 times, and our best test case came out with an R correlation value of 0.94 and a root mean square error of 0.35. And this is our correlation graph. The y-axis got cut off, but they're both plasmaspheric logarithmic electron densities. The bottom is the model's predicted electron values, and the left, like I said, it's cut off, is the actual data from the ERACE satellite. Anyway, so now that we trained the model, we chose 5 of the most promising models out of about the 500. And so we wanted to apply it to some events that were outside of the test data set. So we decided on using 4 separate geomagnetic events from 2013 that were selected in a modeling challenge. And each one of these events is a different type of geomagnetic event. And it's a combination of what is known as a storm or non-storm type event and an energetic electron enhancement or dropout. But this is just for nomenclature purposes to identify each event, and we are not focusing on the energetic electrons. We are just predicting the low energy and cold electrons in the plasmasphere. So before I go to the events, this is just an example of one of the graphs that you will see in the next few slides. So the top graph is our solar wind drivers in a time series plot. The red is the proton density of the solar wind, the blue is the flow speed. And the second graph are ground-based geomagnetic measurements of the magnetic field. And these top 2 are not inputs into our machine learning model, and they're not predictions from our machine learning model, but they give good indications of when a storm begins or an event begins. Now, third graph is our machine learning model's prediction of equatorial electron density in the plasmasphere. And it is time versus L shell. The darker blue regions show that the plasmaspheric electron density is very low, while the orange, reddish, and yellowish regions show where the density is high. And then in the fourth graph, we have the erosion and refilling rate. The blue areas are where the plasmasphere is eroding, and the red areas are where the plasmasphere's electrons are recovering and filling back up. So the first event was from March 16th to the 20th in 2013. And this is what is known as a storm type electron enhancement event. But again, it's important to note that that is just an identifier for this event. So the first thing I like to point out with this event is how stable these solar wind drivers are, and how the prediction kind of reflects that sort of stability here. The plasma pause is really this barrier here where the density drops off, and it's relatively stable. But when this storm begins, as we see with the proton density and flow speed increasing, there is the plasmasphere and the plasma pause begin to shrink, and density begins to be eroded at 4 to 6 L shells. Now, what is happening here is that during an event like this, the electric fields around the Earth are compressed and contract due to the solar wind. And the contraction causes the plasma pause to also be compressed. And when this happens, the electrons in the outer plasmasphere are lost to the solar wind. And this physical process, well, it is consistent with what we see in the model. We do see what looks like a compression of the plasmasphere down to about 4 L shells. And we can see that about 24 hours after the storm starts, which is about here, we see the plasmasphere begin to recover and refill, which means that compression, whatever is driving the compression of the plasma pause, is weakening and the plasmasphere is able to recover. So our second event is what is known as a storm type dropout event. It was from May 30th to June 5th, 2013. And the first thing to note is, again, the solar wind drivers, the proton density is actually significantly higher here than in the previous event. And nonetheless, we still see a significant drop in the plasma pause from what looks to be nearly 8 L shells down to about 4. And in this type of event, it's not the electric field that causes the plasma pause to contract. It's actually the magnetopause that contracts. And this is known as magnetopause shadowing. And the magnetopause compresses the plasmasphere. And in a similar way, the plasmasphere loses its outer electrons. And this prediction is again consistent with that physical process. And I think an important thing to note is how long it takes for the plasma pause to recover back to higher L shells. And by the time this event is over, it is still recovering. And just to reference back to this first event, the plasma pause was recovering relatively quickly. And here, even by the end, it has not recovered to these original values at all. So the third event is a non-storm enhancement event, as it's known. And it is from the 17th of September to the 25th of September, 2013. And again, note the solar wind drivers this time are a lot weaker. And that is also reflected in our equatorial density prediction. The dip in the plasma pause is much shallower, and it doesn't reach below 5 L shell. And while it still compresses, it is consistent with a weak non-storm type of geomagnetic event. And by the end of the event, the plasma sphere is almost completely recovered here. And then our fourth event is another non-storm type event. And as an event one, seen in event one, I want to point out the stability of the solar wind here, and as well as the stability in the equatorial density. This is a good indication that our model can predict dynamic changes in the plasmasphere like in event 2, but also predict the long-term averages of the plasmasphere like we see in older linear fit type of models. But this event, it's a bit harder to describe physically because we're not entirely sure of the physical process behind these non-storm type dropouts, as they're called. But nonetheless, we still see a slight drop in density, but it is a very shallow drop again, and it quickly recovers back to its original, the plasmasphere recovers back to its original density and L shell relatively quickly. So to summarize, the 5 models we chose showed very promising results. They were able to dynamically predict changes in plasmaspheric density, plasma pause, contraction. But at the same time, we believe that this model is also reliable for long-term predictions during quieter solar and geomagnetic conditions. So overall, this model has great potential in the forecasting of space weather and in the forecasting of killer electrons, because again, these cold electrons can influence killer electron acceleration. And it can also grant more insight on the dynamics of the plasmasphere that traditional non-machine learning models may not be able to. So in the future, I plan to add actually ion species data from the HOPE instrument of the Van Allen probes, and I will use that to predict hydrogen, helium, and oxygen ion densities, as well as their erosion and refill rates. Predicting electron and ion densities can give a more holistic view of the plasmasphere and a view at the composition of the plasma itself. And with electrons and ions, we can, sorry, I lost my train of thought there. But anyway, there's also improvements that can be made with the model with just the ERG data. We found that at low L shells near the Earth, the ERG data was somewhat poorly calibrated. So that meant that, but it is interesting to see that our model was able to predict with high accuracy, even though the calibration of the data we compared it with and it tried to train off of was not perfect. So hopefully there is improved calibration with the ERG data sometime in the next few months. Otherwise, we will continue with RBSP data and the ERG data we already have. And for acknowledgements, I'd like to thank my mentor, Jiangning, and my co-mentor, James. I could not be here without them. So, and also thank you to the NSF and everyone else.
All right. Any questions?
Hi, great presentation. So this is like a 2-in-1. Why is 2013 so important? And then why were there no events that you chose between October and February?
So this was actually, like I said, it was a modeling challenge, and they were chosen because they already have a lot of quantitative analysis done on these events, so we can compare it to observational data and maybe some other models. And they're also 4 very unique events. They all are a different type of, I guess, electron enhancement in high energy areas of the magnetosphere. So we felt that they were it was dynamic inputs that would be good to use as a litmus test to how this could predict in differing conditions. And yeah, so the October to February thing, that was mainly just the events chosen by this challenge.
I have a question about so you said that 5 models out of 500 were found to be promising. And I was wondering, was there any commonalities between these models and the number of hidden layers you used or activation functions?
Yeah, so we found that a lot of these models that we used had a similar number of neurons used in each layer. I don't know as much about the weights, but for example, our best model was this one, and the other 4 models that we chose had very similar test graphs to this. And also for the number of layers, I think the best one chose around 500 neurons for the first layer, above 100 neurons for the second layer, and then the third layer chose 2. So it was very interesting seeing what the model thought was the optimal way to predict the densities.
Any other questions? All right, let's thank our speaker again. All right, folks, so you're going to have now a 1-hour break for lunch. We're going to meet back here at 1:15. And our next talk is going to be Bryce. So Bryce, maybe come a couple of minutes early to get set up with the mic and everything. Folks online, we'll see you back here at 1:15. Thank you.